Okay, is there any question from the previous week lectures? Is there any question from the last few weeks lectures? Is there any question from previous few weeks? So what I have done, I have uploaded the coursework. You may have already seen it, Learn. Yeah. And today, so I have already given the coursework in Learn, and here is a handout. I will give you 5 minutes to read the coursework and ask me about the questions or how would you interpret this coursework. So you're welcome to ask me questions on that. Then I will start the lecture. Yeah. Take your time to read the coursework. So the figures are not very clear, isn't it? So what I will do, I will try to project the figures so that you can read it on the screen. That is the coursework. Okay. So what it is, here what you can see is a bridge. What happened here? Anybody? What happened here? So the bridge did not collapse, but we had in some places a big, right? substance, yeah, settlement. So the bridge foundations settle differentially in the whole bridge. So what that has done, that has essentially in some places even by 1 meter or 0.8 meter, right? So is the bridge workable? Of course not, but people can actually, you can be careful, you can cross in some places, you can cross, there's a walk, it's not a complete collapse. There will be downtime, so the bridge is not operable. Probably it will take 6 months or 3 months, or in some places can be 2 weeks, depending on the insurance claim and how you do it, the way how you procure things. But you can make it to work in a relatively short time. You can close some lanes. This is from one earthquake, right? But so this is this year's coursework. But what I want you to do is in the past 3 years, I gave other failures. They are given here. So you can see there are 3 bridges. So in this case, will it work at all? Nothing. So it can't even walk through the, can't even do it. So, and this will take a lot more time to get it sorted, right? They're all on deep foundations, some sort of pile foundation, right? So the coursework is about what you should check. So as a designer, when you're doing a design, you don't want either of these. You don't want either of these, right? You don't want either of these. But in some cases, if you think that actually the earthquake may not occur in its lifetime, there's a very small chance, and if you want to implement all the mechanisms, it might be very expensive. So you might say, well, I will allow for a 1 week or 2 week downtime, and I will try to have I will allow some damages, so that I can easily repair and bring it back. Say for example, in one case, say to avoid this sort of failure, it takes 1 million to do the whole bridge, as an example. But if you want no collapse, plus no settlement, nothing, absolutely, it will cost say 4 million, extra 3 million. But then the chances that the earthquake may not come, there's a chance that it will come in 5%. In lifetime. So would you spend 4 million or you spend 1 million and take the hit? Right? And these are known as performance-based engineering. So they're the new way of designing, performance-based. So do you want a complete collapse? Do you want a certain amount of time, a downtime? And depending on things. And you will say actually I don't mind losing a bridge if it fails, it's fine. Right? Because the costs go up. To have all these things implemented, cost goes up. Okay? Now, tell me is there any question on the coursework? The deadline is 1st of May, right? 1st of May is the deadline. 1st of May.
No.
I think on SOLEARN it used to say 9th of May, but then it got changed to the 1st of May. I think maybe last year it was the 9th of May.
Right.
Yeah, it's the 1st.
So what I gave you, I gave the last year's course to give you a feel about because many of you will come to the first day lecture to see what's being taught and what whole thing. So I give them everything there, just for them to understand. But now I've taken out the last year's course, what we gave you. That was mainly to give you overall what the course is about. Okay. Is there any question on the coursework? I've tried to reduce a lot in this year. Okay, very because I know that what I have done instead. Let me know your brief, then I will interpret it for you.
Can I just ask quickly, with this layout of the question, just to clarify, the liquefaction analysis is with the first case study,
Yes.
and then you're comparing it to the last case study. Is that in question C?
Question C
So
is, okay, now what I want to do, I will give you sample coursework from last years,
okay.
last 3 years, when they've done a good thing. So what you can do, you compare and contrast with this failure and the other failure. What I just said, we will look, here it is a complete collapse, and what mechanism govern these failures, and what mechanism is governing the bridge what you analyzed.
So we can summarise the previous courses that you give us,
Yes.
and then compare that
Yeah.
analysis.
So what I want, learning outcome, you read the failure, why it failed, those 3 bridges. You read them.
Okay.
Read and you sort of take it in the important things. And you write down that, those mechanisms, and you add the another mechanism, which is this. Yeah, it's more about learning from these failures. If you look into codes of practice, what do they do? Codes of practice assumes engineers can miss out something. So they try to give you a prescriptive way how to do analysis. Often they miss out. Often they miss out a mechanism. Often they don't give everything because it's not being identified or not properly documented. But these failures can show actually if they follow all the code of practice, why will it fail then?
For expectation of how long this course will be per question, can you give some?
I said it's short, short report is good, but try to use external diagrams to explain.
So a short half page or is it a short page?
Can you read a half page now? You can. So,
So-
you would at least need to explain this bridge. You can take this bridge pictures, a ground profile, liquefaction depth. So I would say you would need around 15 diagrams to explain the whole thing, right? And so 15 sort of, roughly, what I would say is the bridge, the location of the bridge, some features which you have explained, right? So effectively, you got to use all these diagrams here. So I have already given you how many? 1, 2, 3, 4, 5, 6, 7 diagrams. You also need another 3 diagrams for 3 bridges, 10 diagrams. You had another 5 of yours, at least, maybe more. And run a commentary, mainly on the mechanism why it failed, and you do one calculation about the depth of liquefaction. And then you can compare from the other bridges, okay fine, there they had this, there was a safety against this. So you read this report and from there take out the information and then say probably this will not fail by this because of this. Okay?
Sorry, learn that your technical course will due date is on 24th
Fees.
Is it that would be Wednesday? Okay, there are 2 courses.
Yes, the structure is in the 1st of May, but the technical is in 24th of April.
Is it given in Saturday?
Yes.
Right. In that case, we want to do both, or have to do both. I can change it. I can change it to right. Do you want to? I can change the date first of May, or do you want to
make it as long as you want.
What do you want? You change it first of May, first of May?
Yeah.
So both of first of May, yeah? Is it okay? Yeah. So there are 3 bridges. One is this one. Rio is that bridge. This is consumption bridge. That one is the big is a public good. Yes. Yes. But it is, in
What person?
In the
I was thinking I'll leave that down as long as it's in future. Yeah, I've got Wednesday that I
last year's course was very high. Not very much. Just main mechanism.
Oh yeah, you go straight.
Yeah, so I'll give you everything is so you get the answer this bridge. So it means about learning. You would learn this language. Let me give you in your head what you want.
Ages ago, or almost
Is there any other question?
Some go do that. To go crash it first. And then I don't really need to I need to go.
Okay, so let's start.
Immediately go.
Right.
Yeah.
I'm pretty sure they're right.
Yeah, just
Okay, I will help you with the proof, okay? Right. Let me start this one first. Last week I gave you a course handout about regression depth and example problems.
I'm pretty sure I'm done at the moment.
So, what I will do, I know you are late, so I didn't start yet.
I had it with Omar.
See? How was the phone interview?
Around that.
Clear?
Because the conversation scared me earlier.
Yeah, no.
Okay. So, you can see here the title, code efficiencies. Means, so it means that what I am giving you hint is that codes are often deficient. Codes doesn't cover all the mechanisms, right? And that's the main point about this case study. You will see that the codes somehow couldn't cover this particular case, and engineers followed the procedure and they missed one particular mechanism. Okay. Right. So here are some of the examples of pipe failure. So what you can see in this case, there is a pipe supported building. The building is intact. In both cases, they are intact and pipe supported, and you can see what happened to this building. And here is a bridge on pipe functions. Right? So why things fail? Just remind you that if you have a fault rupture, you can get a big sort of settlement, big ground can. So this building, what you can see, so the picture second there. So this building narrowly escaped, and the road had a similar fate. But what they did, they put a ramp there and started to operate because you got to start the communication, right? So this coursework is something around these lines. You can have some movement and that can cause some difficulties. Now, the problem, what I was showing you before, is all those structures, they are supported on pile foundations. And what are piles? For those of you who are not geotechnical, piles are basically long slender column. You put it into the ground so that you have the load transfer to deeper competent layer. So if I, for example, if I put the building on this top of the layer, it may have been fine, but actually you may have settlement, tilting, but you found out that here's a very good competent layer. So you put the pipe to take the load to deeper layers. Now, what happens in an earthquake? In earthquake, what happens? Say you start your, say the earthquake starts. So, if we look into a stage where there is no earthquake, so the vertical load is balanced by the reaction in the pile support unit. Yeah? So the pile are taking the whole building load. In a very simple sense, if you know the vertical load of the whole building, and if you know the number of piles, you roughly get what is the vertical load on each pile. However, when earthquake starts, what happens? As earthquake starts, this whole ground starts to shake. As the whole ground starts to shake, you also have the building shaking as well. Right? And in that case, what happens? The building wants to rock. Because the building vibrates. As the building vibrates, it then rocks. It applies more vertical load on the pile. That is P gravity plus V inertia. So vertical load due to inertia. That comes due to building inertia. Because the building wants to vibrate. As the building wants to vibrate, it will be like a moment. And that moment is taken by the pile. Just to give you a simple estimate, how can you find out the extra vertical load on the piles? Any idea? You have done you have done response spectra, isn't it? Stefan told me he has already taught response spectra. So how can you apply? Okay. What are the response?
Do you get the response spectrum to give you the displacement of the ground at that point, and then use that displacement maximum?
Right. Let us go back and see what does a response spectra plot. So what do we plot with the response spectra? Yeah.
You need to take the forces due to the masses
Yes.
and calculate the moment on the base of the building.
Yes. Yeah. That's right. So what are the response spectra plot? What are these axes? This is.
That's time.
What about this axis?
That's time.
What's time? Time period.
Time period. Yeah.
What's time period? Time period means what? What does time period mean?
Period of building.
Yeah, so it's basically the natural frequency. Natural frequency. Frequency and one frequency is time period. Yeah? This is building natural period. Means if you give a small movement, a perturbation, it will swing its own, and what is that frequency? Right? And what is that axis?
Acceleration due to gravity.
Spectral acceleration. Spectral acceleration. Yeah? SA. Right? So the code, every code, that all codes give you these graphs, and they actually look something like, so they look something like that, isn't it? So all code gives you this, and this spectrum depends on the type of ground, hard soil, soft soil, whatever type of soil is, you get graph like that. So what it shows, if you know the building time period, you can get one point from here, and if you read off this thing, it will give you the building's acceleration, spectral acceleration, right? Say for example, this building has got a period of say 0.5 second. You come up here, 0.5 second, for the particular ground where it is found, work out acceleration. Suppose you get 0.2 g or 0.3 g. That is acceleration. You know the building mass, multiply by that loosely will give you the inertia. Yeah? Okay? So that will give you the inertial load, right? So once you know the inertial load, you can find out the moment there, isn't it? It's a push-pull action. So moment, that moment by this lever arm spacing will be the force on each pile. Right? That's the extra force coming onto your pile, vertical load coming onto your pile due to the rocking motion. Yeah? So that's why we say peak gravity. Peak gravity is always there. Gravity is always there. There's a building's dead load. Can be a bridge dead load. You have the extra vertical load coming due to rocking motion, right? That's inertia effect. So, when it occurs, it starts to occur immediately, right? As the earthquake starts, depending on the earthquake, this thing will change. So that's not a fixed number, that changes as the earthquake progresses. What does the ground do in that period? The ground starts to liquefy. It may. In soil that liquefy, it will liquefy. So it will start to liquefy and gradually go down and down. Right? So as it liquefies, so the pile is no longer stiff. In this case, the pile was surrounded by a heavy, strong material, right? A strong sand grabbing it. But as the soil is liquefying, the pile is simply becoming like a column, like a normal column. Right. So, if you want to, right, so that's one case. And then, what you might find is that this ground here, near a river, so the soil liquefies. What it will stop it from flowing? Nothing. It starts to flow. The ground will start to flow. As the ground starts to flow, it starts to apply more lateral load. Right? So, if you were a designer, what would you check for? All these mechanisms? Right? So, that means to start with, if you find out that the ground will not liquefy, so you can forget these two mechanisms. Right? Yeah? If it doesn't liquefy, you don't worry about this and this. You only worry about this one. And if it liquefies, you can start to worry about what happens here and what happens there. Right? So that's one of the important thing is to work out, keep the ground liquefied, and if it liquefies, to what depth. Right? And they can do all these mechanisms. There are a bit more complexity also on that as well. Here is the pile, and as you apply a vertical load, so each pile will have the load transferred to the soil by two mechanisms, the friction and the end bearing. Right? So the friction is the friction on the pile skin, so the shock resistance. And this shock resistance is a function of vertical effective stress. Right? Those who are doing deformation, they already have done this. But for the rest, I will explain this particular mechanism. So if you have a pile and it goes down to that depth, so the pile will have a load, that's a ground level, okay? That's a ground level. The load is being taken by end bearing and friction on the side. Now, how do I calculate the friction resistance? So, say for example, I am looking into only this particular element of this point. So, you can easily compute the vertical stress. So, sigma V dash. Then you can calculate the lateral stress by multiplying by a earth pressure coefficient. and then you can compute this one friction by multiplying this by the angle of friction of the pipe and the soil. So this friction will be given by K sigma G dash times tan delta, and then you take the area of the circumference. So the main thing is that the friction is a function of sigma V dash, that's the vertical effective stress. By definition of liquefaction, sigma V dash is 0. So liquefaction means the ground, by definition, sigma V dash is 0. Therefore, if it liquefies, you lose this friction and you see a settlement. This is what happened in the Juan Pablo Bridge, the course. What happened? So if the ground liquefied to a certain depth, then it started to have to settle. So the pipe is having the top vertical load of the bridge depth. Right? So the pipe has got the vertical load from the bridge depth. And earlier, the whole pile was being grabbed by the soil. But with liquefaction, some part gave up. So you had a circle. Yeah? Okay? Okay, so this is, so as it liquefies, you have a skin friction will diminish, then the axial capacity will reduce. Because the axial capacity of a pipe means how much load it can carry will reduce, because you are losing the part of the shaft capacity in the layer that will liquefy. Yeah? Okay? And so you have, so therefore this may lead to bearing capacity failure or settlement failure. Bearing failure means that suppose the pipe ends in the liquefiable layer, so you didn't go beyond the liquefiable layer. So what will happen? You will simply sink. Nothing to stop it, isn't it? That's what it is. Okay? Okay. Now another interesting thing is, let's consider the building period for this condition. In this particular condition, you have the building, you have the pipe, and the soil intact, and the foundation. So the building period is normally dependent on only the building characteristics. So did you find out the building period by some simple equations? Did Stefan cover that? How do you have the building period? Is there any formulas? Exactly. So right. Yeah. So that can be CH and H0 or something, or can be 0.1 times n. N is number of floors, right? Is there any? So the building period T is something CH, some coefficient times height to the other some numbers, right? So what does it consider? It considers only the building dimension, isn't it? Consider the building dimension, right? Why there is nothing about ground or foundation? So does this formula distinguish if it is a shallow foundation or a deep foundation? Does it consider? What does it mean? It means, it assumes this is very, very strong, rigid, and this is only flexible. So it assumes that the building is flexible compared to the foundation. Foundation is so rigid, it doesn't take part in the vibration. Right? What it means that the foundations are very rigid. So in that case, you don't take into account the formulas the formula don't take into account anything to do with the foundation. However, when the soil liquefies, we have to take into account all these things. So this is a model at no liquefaction. But when soil liquefies, the model will become, same model will become and say if it is a pile formation and say that's the depth of liquefaction to what depth it liquefies. So the pile then starts to become, a model becomes like this. So you have got extra one there, and this is, the model becomes like that. In effect, what it is showing, just give example, say for example you found out that the building period is a 0.5 second, right? When it liquefies, it will become a bit more slow. So it will become say 3 seconds, 4 seconds. The time period will increase. So the foundation becomes more flexible. Yeah? How does it impact? How does it impact your design? Remember, you were using response spectra for doing the force separations. So you are taking the building period, which was 0.5 second. When it liquefies, the building becomes more flexible, goes to 3 seconds. So then again go back and check in the response spectra where it is going. So what it means that so you were say somewhere here, and as it liquefies, say this is 0.5 second, it goes to say 3 seconds.